Chapter 4, Common Logarithms. Now consider this indexed number. 3 raised to power 2 is equal to 9. On the chapter on indices, we called the power 2 an index. For purposes of this chapter, this index has another name. It is called a logarithm. 3 is called the base. A logarithm is simply the power to which a given base is raised to give a particular number. In this case, we say that 2 is the logarithm of 9 to base 3. In shorthand, we write log to base 3 of 9 is equal to 2. Can you translate this into index form? Log to base z of x is equal to y. Have you done that? So z is the base, and it is raised to the power of y to give x. And so we have z raised to y is equal to x. Numbers that are multiples of 10, like 10 itself, 100, 1,000, and so on, can easily be expressed as powers of 10. And so 10 raised to power 1 is equal to 10. That means log to base 10 of 10 is equal to 1. 10 raised to power 3 is 1,000. That means log to base 10 of 1,000 is equal to 3. 10 raised to power 6 is 1,000,000, which means log to base 10 of 1,000,000 is equal to 6. When the base is 10, we use the term common logarithm. All other numbers can be expressed as logarithms to base 10. Let's try 2, for example. Get a calculator and try this. 10 raised to the power of 0.3010. It will surprise you that 10 raised to the power of 0.3010 is equal to 2. We say that log to base 10 of 2 is equal to 0.3010. Trying with 3, we get 0.4771. And so 10 raised to the power of 0.4771 is equal to 3, meaning that log to base 10 of 3 is equal to 0.4771. When dealing with common logarithms, the base is often omitted, and so we would simply have log 2 is equal to 0.301 and log 3 is equal to 0.4771. Mathematical tables of logarithms of numbers provide logarithms of natural numbers from 1.000 to 9.999. They look just like the other tables we have seen before and are read the same way. In these tables, the differences columns indicate add. The logarithms of numbers between 1 and 10 are read directly from the tables. For instance, log 2.463. We go to the tables. 2.4 is here. Next is 6. The column of 6 will meet us here. Notice that the numbers begin with 0 point, and so this is 0.3909. We proceed to the differences column. 3 will meet us here, and we have 5. So we add, and we shall get 0.3914. And so log 2.463 is equal to 0.3914. That means 10 raised to the power of 0.3914 is equal to 2.463. For numbers greater than 10, we first write them in standard form. For example, log 349.3. In standard form, it is 3.493 times 10 raised to the power of 2. Log of 3.493 first, 3.4 is here. The column of 9 will meet us here, and we have 0.5428. Differences columns, 3 will meet us here, and we have 4. So we add, and we shall get 0.5432. Next is the log of 10 to power 2. Now, this is important to get. We have already indicated that the log of a number is simply the power of that number. And so the log of 10 to power 2 is simply 2. So we add 2 to our answer as a whole number. And so we shall have 2.5432. And so log 349.3 is equal to 2.5432. In fact, after you write the number in standard form, you write the power of 10 first, even before you read the logs. Let's have another example. Log 39. In standard form, that is 3.9 times 10 to power 1. The power of 10 is 1, and so log of 10 to power 1 is 1. We write that already even before we go to the log of 3.9. 3.9 is the same as 3.90. 3.9 is here. Next is 0. The number is 0.5911, and we add it to 1. So we shall have log 39 is equal to 1.5911, and so on. Numbers less than 1. Again, for these numbers, we first write them in standard form. For example, the log of 0.514. In standard form, that is log 5.14 times 10 raised to power of negative 1. The log of 10 raised to power negative 1 is negative 1. The log of 5.14, we have 0.7110. Pause for a moment. Notice that the log of 10 raised to power negative 1 is a negative, but that of 5.44 is a positive. If we give the log of 0.514 as negative 1.7110, it will be misleading, because this way we shall be indicating that the entire figure is a negative, but it is not. What we do is that we write the negative sign above 1, so we say it's 1 bar, and that's the logarithm of 0.514. How about 0.03671? In standard form, that is 3.671 times 10 raised to power of negative 2, and the log of everything. The power of 10 is negative 2, so we start with 2 bar. And then we go to the log of 3.671. 3.6 is here. 7 will meet us here. We have 0.5647. Then to the column of 1, and the number is 1. We add and we get 2 bar 0.5648. In a logarithm, the integer part before the decimal is called the characteristic, and the decimal part is called the mantissa. Anti-logarithms. Now, anti-logarithms are simply the reverse or the inverse of logarithms. And so if log 2 is equal to 0.3010, then the antilog of 0.3010 is 2. This is written as log inverse of 0.3010 is equal to 2. antilogs of numbers are read from the antilog tables. For instance, that antilog of 0.3010. We go to the antilogarithm tables. We locate 0.3 in the x column. Then go to the column of 1. They coincide here and the number is 2.000. How about the antilog of 1 bar 0.4771? Now, the fact that we have a 1 bar means that we had 10 raised to the power of -1. This is the antilog of 1 bar. Then we find the antilog of the mantissa, 0.4771. If you go to the antilogarithm tables, that is 3.000. And so the antilog of 1 bar 0.4771 is 3 times 10 raised to the power of -1, or simply 0.3. If it was 1.4771, then we would have 3 times 10 raised to the power of 1, or simply 30. Applications of logarithms. Now, logarithms are used in working operations of numbers in multiplication and division. In the chapter on indices, we saw that when multiplying indexed numbers with common bases, we add the powers. When dividing, we subtract the powers. Here now, we are saying that common logarithms are powers to base 10. So the same laws of indices will apply. And so a times b is equal to the log of a plus the log of b. A over b is equal to the log of a minus the log of b. For example, 4.53 times 3.94. This is equal to the log of 4.53 plus the log of 3.94. From the tables, log 4.53 is equal to 0.6561, and the log of 3.94 is equal to 0.5955. When we add the two logs, we get 1.2516. Finally, to get the real numbers, we find the antilog of this answer, and so log inverse of 1.2516. And so our answer is 1.782 times 10 raised to power 1, or 17.82. What of 53.31 divided by 0.391? This is the same as log 53.31 minus log 0.391. For the first one, we start with 1 point. Put it here, and we shall have 1.7268. Next, start with 1 bar point. So we have 1 bar 0.5922. Subtract the two logs. We shall have 6 here. We have 4, 3, 1. And then we have 1 minus 1, and that gives us 1 plus 1, which is equal to 2. Finally, the antilog of 2.1346. And so our answer is 1.363 times 10 raised to power 2. Now, in indices, we saw that to find the square root of an indexed number, we divide the power by 2. Here again, we divide the logarithms by 2, or multiply by a half. That is to say, the square root of a is equal to a half the log of a. For instance, the square root of 1.43 is equal to a half times log 1.43. That is equal to a half times the log of 1.43 is 0.1553. That gives us 0.0777. Then the antilog of this, and we shall have 1.196. For squares, we multiply the log by 2. That is 2.45 squared is equal to 2 times the log of 2.45. For cubes, we multiply by 3. That is 3.94 cubed is equal to 3 times the log of 3.94. Cube roots, we divide by 3. So the cube root of 1.49 is equal to a third times the log of 1.49. Finally, we work out this huge example. Without using a calculator, evaluated this. Now, we won't be going back to the logarithm tables to save on time. We'll just work this one out. Now, when working out such a long process, it's easier to arrange your work in an orderly manner. So we start with the numerator part. We shall have numbers here and their logarithms here. 4.592, the logarithm is 0.6620. 0.521, the log is 1 bar 0.7168. 16.25 is 1.2109. We are multiplying the numbers, so we add their logs. That gives us 1.5897. We go to the denominator now. 3 squared, the log of 3 is 0.4771, and because we are squaring, we multiply that log by 2, and we shall get 0.9542. 2.44, the logarithm is 0.3874. 3.31, the log is 0.5198. 0.04, the log is 2 bar 0.6020. Again, we are multiplying and we add the logarithms. So we shall have 0.4634. Now we divide the numerator by the denominator, and so we shall subtract the logarithms. If we do that, we shall get 1.1263. And then we are required to find the cube root of the entire figure, and so we divide the logarithm by 3. So we shall have a third times 1.1263, and that gives us 0.3754. To get the real numbers, we finally find the antilog of these, and so the log inverse of 0.3754 is equal to 2.3737. Good luck with logarithms.
The way we teach it in university and in high school as well, and colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor.